Let's break down the core idea behind this paper. QLoRA, efficient fine-tuning of quantized LLMs from the University of Washington. This is the paper that made it possible to fine-tune a 65 billion parameter model on a single GPU without losing any quality. By the end, you'll understand every trick that makes that work in FP4, double quantization, and paged optimizers. Here's a number that sounds made up. To fine-tune a 65 billion parameter language model the normal way, in 16-bit precision, you need more than 780 gigabytes of GPU memory. That's not one GPU. That's a whole rack of them, tens of thousands of dollars, out of reach for basically everyone outside a big lab. QLoRA takes that exact same 65 billion model and fine-tunes it on a single 48 gigabyte GPU, the kind you can rent for a couple of dollars an hour, with no measurable drop in quality. The model they trained this way, Guanaco, reached 99.3% of ChatGPT's score on a popular benchmark, after just 24 hours on one GPU. Over the next half hour, we're going to build every piece of how that's possible. First, where does that 780 gigabytes even come from? 3 places. The weights themselves, 65 billion parameters in 16-bit is 130 gigabytes, just to hold the model at rest. Then, to train, you need the gradients, one number per weight, another 130 gigabytes. And then the optimizer. Everyone uses Atom, and Atom keeps 2 extra running statistics for every single weight, a momentum and a variance, which is 2 more full copies. Stack it up. Weights, gradients, and optimizer state, and you're carrying the model something like 6 times over. That's how a 130 gigabyte model becomes a nearly 800 gigabyte training job. The weights are the small part. The training bookkeeping is what actually kills you. Now, there's an obvious idea for shrinking a model, quantization. Instead of storing each weight in 16 bits, store it in 4. That's 4 times smaller. And it works beautifully for inference, for just running the model. The problem is training. Gradients are tiny, delicate signals, and when you try to backpropagate them through crudely rounded 4-bit weights, the math falls apart. The updates get too noisy, and quality collapses. So the state-of-the-art was a hard split. You could quantize a model to run it cheaply, or you could fine-tune it at full precision expensively, but you could not do both. QLoRA's entire reason for existing is to erase that line. The authors are blunt about the gap they're closing. The first half of QLoRA's name is LoRA, so let's make sure that piece is solid. Normal fine-tuning updates every weight in the model. LoRA doesn't. It freezes the entire pre-trained model, completely untouched, and bolts on a pair of tiny, skinny matrices next to each weight matrix, an adapter. During training, only those little adapters learn. The giant frozen model just passes gradients through to them. Because the adapters are a fraction of a % of the model's size, you're now training a few million numbers instead of billions. The layer's output becomes the frozen result, plus the adapter's small correction. That's LoRA. Freeze the giant, train a tiny detour. QLoRA keeps all of that and adds one radical move. Here's the radical move, and it's deceptively simple to say. LoRA froze the base model, but it still stored that base in 16 bits, so a 65 billion model still eats 130 gigabytes of memory just sitting there frozen. QLoRA asks the obvious question. If we're never going to update those base weights anyway, why store them at full precision? So it quantizes the entire frozen base model down to 4 bits, cutting that 130 gigabytes to about 33, and then trains the 16-bit LoRA adapters on top of it. Gradients flow backward through the frozen 4-bit weights into the little adapters. The base is 4-bit storage. The adapters and the actual computation stay 16-bit. Simple to state, but making it truly lossless takes 3 genuinely clever tricks. Here's the whole memory picture on one chart, and it's the map for the video. On the left, full fine-tuning, the 16-bit model, plus gradients, plus the fat atom optimizer state, a towering bar. In the middle, plain LoRA. The base is frozen, so we drop the gradients and optimizer state for it. But the base is still 16-bit, so the bar is still tall. On the right, QLoRA. The base model is squished to 4-bit. The optimizer only tracks the tiny adapters, and paged optimizers shave off the last dangerous spikes. The bar finally drops under 48 gigabytes. 3 innovations get us from that middle bar to the right bar: an F4, double quantization, and paged optimizers. Let's take them one at a time. To understand the tricks, we need to understand quantization itself, concretely. Say you have a block of weights in full precision and you want to store them as 4-bit integers, which only have 16 possible values. You find the largest magnitude in the block, call it the abs max, and you use it to rescale everything so the biggest value maps to the very top of your 4-bit range. Multiply by that scale, round to the nearest of the 16 levels, done. To get the real number back later, you divide by the same scale. That scale is called the quantization constant, and you have to store it alongside the block. Quantize, round, and keep the constant so you can undo it later. That's the whole primitive. But there's a catch that ruins naive quantization: outliers. Suppose one weight in your block is huge, and all the rest are small. The abs max is now set by that one giant value. So when you rescale, all the small weights get squashed into just 1 or 2 of your 16 levels. You've wasted almost your entire budget of levels on empty space around the outlier, and the many small weights, which actually matter, are now indistinguishable from each other. The standard fix is blockwise quantization. Don't quantize the whole tensor at once. Chop it into small blocks, say 64 weights each, and give every block its own constant. Now one outlier only ruins its own little block, not the entire tensor. Hold on to this idea, small blocks, because it comes back. Now the first real innovation. 4-bit integers space their 16 levels evenly, like a ruler with equally spaced ticks. But neural network weights are not spread out evenly. If you actually look at them, they're bell-curved, a normal distribution, tons of values clustered near 0, and very few out in the tails. So an evenly spaced ruler is a terrible fit. You're spending the same number of precious levels on the empty tails as on the crowded center where almost all your weights live. What you really want is a ruler whose ticks are packed tightly where the weights are dense and spread out where the weights are sparse. In other words, a data type shaped like the weights themselves. The principled way to build that ruler is called quantile quantization. The idea: place your 16 levels so that each level, each bin, gets an equal number of weights assigned to it. Densely packed region near 0, put lots of closely spaced levels there. Sparse tails, just a few widely spaced levels. This is provably information theoretically optimal. Every level carries the same amount of information, none is wasted. Beautiful in theory. The problem is that finding those exact quantile boundaries means scanning your data and estimating its distribution, which is slow, and the fast approximations you'd reach for instead are inaccurate exactly where it hurts most, out on the outliers. So quantile quantization is optimal, but done naively. It's too expensive to actually use. QLoRA's trick is to make it cheap. Here's the insight that makes it cheap, and it's lovely. We don't need to estimate the distribution of every block, because we already know its shape. Pre-trained weights are, reliably, a zero-centered normal distribution, just with different widths in different blocks. And blockwise scaling by abs max already normalizes each block into the same range. So every block, after scaling, has the same shape, a standard normal, squeezed into -1 to +1. That means the optimal quantile levels are identical for every block, and you can compute them once, exactly, from a theoretical normal distribution, with no per-block estimation and no scanning. You pre-compute 16 levels shaped like a bell curve, and reuse them for the entire model. That fixed, pre-computed, bell-shaped 4-bit data type is NF4, NormalFloat 4. Information theoretically optimal and essentially free. Let me make NF4 tangible with an actual block. Take 64 weights. Step 1. Find the abs max and divide, so the block now lives in -1 to +1. Step 2. For each weight, snap it to the nearest of the 16 NF4 levels. And remember, those levels aren't evenly spaced, they're bunched near 0. So a weight of 0.01 gets a fine-grained level right nearby, while a rare weight near the edge shares a coarse level out in the tail, which is completely fine because there are almost none out there. You store, per weight, just the 4-bit index of its level, plus one shared constant for the whole block. To use a weight, you look up its level and multiply by the constant. 16 levels, placed exactly where the weights actually are. One subtle but important detail. A symmetric set of levels, evenly split around the middle, doesn't actually include an exact zero, and that matters, because padding and masked out values are exactly zero, and you want them to quantize to zero with no error at all. So an F4 is built asymmetrically. They compute the levels for the negative side and the positive side separately, then merge the two sets and drop the duplicate zero in the middle. The result uses all 16 codes, and one of them is exactly zero. It's the kind of tiny engineering care that separates a data type that works in a paper from one that works on real models with real padding in them. The abstract states the property directly. Second innovation, and it's quantizing your own bookkeeping. Remember, we wanted small blocks, 64 weights each, to contain outliers. But every block needs its own 32-bit constant. Do the math. A 32-bit number for every 64 weights is half an extra bit per weight, spent purely on the constants. On a 65 billion model, that's gigabytes of memory going to scaling factors. So QLoRA quantizes the constants too. This is double quantization. Take all of those 32-bit block constants and quantize them in blocks of 256 down to 8-bit floats with 1 second-level constant per group. The per-weight overhead drops from half a bit to about 1/8 of a bit, saving roughly 0.37 bits per parameter, around 3 gigabytes on a 65 billion model, essentially for free, with no measured quality loss. You quantize the quantizer. Third innovation, paged optimizers. And this one is about surviving spikes, not shrinking the average. Even with everything else compressed, training has sudden memory bursts, especially when a long sequence hits gradient checkpointing and the optimizer state balloons for a moment. One spike over your GPU's limit, and the whole run crashes with an out-of-memory error, and hours of training are just gone. QLoRA's fix borrows an old operating systems idea, paging. Using NVIDIA's unified memory, the optimizer state is placed in pageable memory, so when the GPU is about to run out, those pages are automatically evicted to CPU RAM and paged back in when they're needed for the update step. It's exactly like your operating system swapping memory to disk. The spikes get absorbed by CPU RAM instead of crashing the job, so a single GPU can finish a run it otherwise never could. Let's assemble the full QLoRA layer in one equation, because every piece we built shows up in it. To compute a layer's output, you take the 4-bit NormalFloat base weight and dequantize it. And because we double quantized, that's a double dequantization. First unquantize the constants, then use them to unquantize the weight, back up to 16-bit. You matrix multiply the input by that, and then you add the LoRA adapter path, the input times the two little adapter matrices, in 16-bit. Output equals the dequantized 4-bit base path, plus the 16-bit adapter path. The base sits in memory as 4-bit in F4. It only becomes 16-bit for the single instant of the multiply, and then it's thrown away. That last point is the key mental model, so let me draw it out. QLoRA has two data types living at once, a storage type and a compute type. In memory, at rest, the base weights are 4-bit in F4, and that's what makes the model fit at all. But you can't do good matrix math in 4 bits. So the instant a weight block is actually needed for a multiply, it's dequantized, just in time, up to 16-bit brain float. The multiply happens in 16-bit, and then that 16-bit copy is immediately discarded. It is never stored in 16-bit, only borrowed for a moment, one block at a time. 4-bit to sit still, 16-bit to do work. That little dance is exactly why QLoRA is both tiny in memory and accurate in computation. And the backward pass is where the savings really land. When gradients flow back, QLoRA only ever computes a gradient for the LoRA adapters, never for the 4-bit base weights. The base is frozen, so it needs no gradient and, crucially, no optimizer state, no atom momentum and variance for 65 billion weights. That is the single biggest memory saving of all. Yes, computing the adapter's gradient requires briefly dequantizing the base weights to 16-bit to pass the signal through them, but nothing about the base is stored or updated. All the expensive training bookkeeping, gradients, and optimizer state applies only to the tiny adapters. The giant model is just a frozen 4-bit lookup table that gradients pass through on their way to the parts that actually learn. The mechanism, stated plainly in the abstract. Quick pause. If quantizing a model down to 4 bits per weight and watching it not lose any quality is the kind of thing that genuinely delights you, then you already know what to do. Like, subscribe, and share it with someone who still thinks you need a data center to fine-tune a model. It really helps the channel. Now, back to it, because the results are where this gets fun. Here's a finding that turned out to matter more than the authors expected. The common way to use LoRA is to attach adapters to just the query and value projections in attention, 2 spots per layer. QLoRA's team found that for large models, that is simply not enough to match full fine-tuning. You leave real quality on the table. The fix is almost embarrassingly simple. Put a LoRA adapter on every linear layer in the transformer block, not just 2 of them. Once they did that, 4-bit QLoRA matched full 16-bit fine-tuning. And here's the surprise. The adapter's rank, how big each one is, barely mattered at all. What mattered was covering every layer. The number of adapters, not their size, is the real lever. You might worry that adapters on every layer blow the memory back up. They don't, and the reason is illuminating. In LoRA training, the adapter weights themselves are almost nothing, tens of megabytes. The real memory goes to activation gradients, the intermediate values you have to keep around for backprop, and with gradient checkpointing, those get managed down to a small footprint too. The point is, the 4-bit base model dominates the memory, and the adapters are a rounding error. So you can afford to be generous, put adapters everywhere, because doubling a rounding error is still a rounding error. That's the quiet reason QLoRA can both fit in tiny memory and fully recover quality. The thing that gives you the quality, more adapters, is nearly free. Now, does NF4 actually beat the alternatives, or is it just theoretically pretty? They tested it head-to-head against 4-bit integers and regular 4-bit floats, measuring perplexity, where lower is better, across a range of models. 4-bit integers came in worst, around 34. Regular 4-bit floats did better, around 29 to 31. And NF4, with double quantization, came in best, at about 27.4. Bit for bit, the bell curve-shaped data type carries more of the model's real information than the evenly spaced ones do. The theory paid off in practice. If you're going to spend 4 bits per weight, spend them shaped like the weights. And here's the headline result, the one the whole paper is built to earn. Across a battery of benchmarks, GLUE, supernatural instructions, and MMLU, 4-bit QLoRA with NF4 matches 16-bit full fine-tuning and 16-bit LoRA. Not close to, not within a few points of, matches. The quality you lose by crushing the model down to 4 bits is completely recovered by training the adapters on top of it. Regular 4-bit floats, by contrast, stayed about a full percentage point behind, which is exactly the gap that NF4 closes. So you get the memory of a 4-bit model and the quality of a 16-bit one at the same time. That's the single sentence this entire method exists to make true. Their summary says it without hedging. With fine-tuning suddenly cheap, they went and trained a family of chatbots called Guanaco, and the numbers are striking. The biggest, Guanaco 65B, fits in 41 gigabytes and reached 99.3% of ChatGPT's score on the Vicuna benchmark, trained in 24 hours on a single GPU. The smallest, Guanaco 7B, needs just 5 gigabytes of memory, small enough for a laptop, and it still beat a 26 gigabyte Alpaca model by more than 20 points. And because fine-tuning had gotten so cheap, they trained over 1,000 models to study it properly, something that would have been flatly impossible at full precision. Cheap fine-tuning didn't just save money, it changed which experiments you can even run. One result deserves to be pulled out, because it flips a common intuition. Given a fixed memory budget, is it better to run a smaller model at high precision or a bigger model at low precision? QLoRA's evidence says, go bigger and lower. A larger model squeezed to 4 bits reliably beats a smaller model at 16 bits that uses the same memory. Quantization, in other words, isn't just a compression tax you pay reluctantly. It actively changes the best model you can fit in your hardware. If you have 48 gigabytes, don't reach for the biggest 16-bit model that fits. Reach for a much bigger 4-bit one. More parameters at lower precision is the winning trade. The cheap fine-tuning microscope surfaced another lesson, this one about data. You'd assume more training data is always better. It isn't, not straightforwardly. A carefully curated 9,000 example dataset produced a better chatbot than a subsampled 450,000 example one, more than 50 times larger. Quality and suitability of the data beat sheer quantity. And relatedly, they found that scoring well on a knowledge benchmark like MMLU did not predict being a good chatbot, and vice versa. What you're training for has to match what you're measuring. The data you pick matters more than how much of it you pile up. One more contribution that's easy to overlook. How do you even score 1,000 chatbots? Human evaluation is the gold standard, but it's painfully slow and expensive. So they ran a tournament. Models play matches, generating responses to the same prompt, and a judge picks the winner, and the wins get aggregated into an yellow rating, exactly like chess. The twist: they used GPT-4 as the judge and found it largely agrees with human raters, making it a cheap, fast stand-in, though with real caveats. It sometimes disagrees sharply, and current chatbot benchmarks aren't fully trustworthy. It's an honest, useful methodology for an era where we're producing models faster than humans can possibly evaluate them. It's worth naming what QLoRA it doesn't claim. They showed 4-bit fine-tuning matches 16-bit LoRA and full fine-tuning at the scales where they could afford to run the baselines. But running a full 16-bit fine-tune of a 65 billion model just to compare against is so expensive they couldn't actually do it. So the very largest comparison rests on the pattern continuing to hold. The paged optimizer prevents crashes, but the paging can occasionally slow training down, and they don't fully characterize when. NF4 assumes the weights really are normally distributed, which holds for pre-trained models, but isn't a law of nature. And you still need the whole base model in memory. 4-bit is small, but it isn't nothing. Real limits, but modest ones against everything it enables. Step back, because QLoRA changed who gets to fine-tune. Before it, adapting a large open model meant a serious multi-GPU budget. After it, a graduate student or a hobbyist with one consumer card could fine-tune models that used to require a server. NF4, double quantization, and paged optimizers were folded straight into the Bit Sandbytes library and Hugging Faces tooling. So today, loading a big model in 4-bit and adding LoRa adapters is a few lines of code that thousands of people run without ever thinking about the machinery underneath. Most of the open-source fine-tunes you've seen over the last couple of years are, under the hood, doing exactly this. It genuinely democratized the thing. Let's put the whole method back together. Start with a giant pre-trained model. Quantize its frozen weights to 4-bit NormalFloat, a data type shaped like the bell curve the weights actually follow, so every one of the 4 bits goes where it counts. Double quantize the scaling constants to claw back a few more gigabytes. Add small LoRa adapters on every linear layer, not just 2, and train only those. During each matrix multiply, dequantize the 4-bit base up to 16-bit just for that instant, then throw it away. And wrap the optimizer in paging, so memory spikes get absorbed by CPU RAM instead of crashing the run. The result: 65 billion parameters, fine-tuned on one GPU, at full 16-bit quality. That, end-to-end, is QLoRA. Here's what I keep turning over. QLoRA works by freezing a 4-bit base and learning a tiny 16-bit correction on top, and it fully recovers quality, which is a strange and wonderful fact. It means almost all of what fine-tuning does can be absorbed by a tiny, low-rank adapter, while the huge base gets brutally compressed and never touched. So how much of a model's precision is actually load-bearing, and how much is just there? If 4 bits plus a small adapter is enough, where exactly is the floor? We still don't really know. That's my read. Tell me yours.